Good afternoon. We are going to start with another part of our course, rigid body mechanics, called dynamics, right? So we have done so far on the modules. Essentially, we looked at rigid bodies which are not moving at all, which are completely constrained, or we looked at problems wherein what are the necessary forces additionally to be added to the system of forces so that the body cannot move. So we were essentially looking at bodies which were under static condition. Just a minute. To keep my phone outside. Yeah. So now we are going to look at our rigid body mechanics, wherein the bodies which are not completely constrained. That means they have some freedom. Then, according to the system of forces acting on it, the effect will be realized. That effect is what is called motion. So, whenever there is a body which is under motion, that body can have an acceleration. That body can undergo acceleration. If a body is moving under motion but does not have acceleration, moves in a straight line, that state also is considered to be a static condition where the motion is what is called a simplified motion called a uniform motion. So, body which is moving in a straight line under motion it is, but it is not accelerated. That means it is going with the constant velocity. In such cases, that is also considered to be one which is under static condition, and system of forces acting on that is equal to 0. That's what we have looked at. Why? Because you essentially understood Newton's three laws of motion. Newton's first law state what? A body will remain in its own state of rest or in moving condition in a straight line unless and until there is an external force acting on it. So otherwise the state will remain the same. That means what? If it is acting, then that external force system is not made to 0, that is made to equal to its rate of change of linear momentum. That's essentially the second law. F is equal to ma. So when F is equal to ma, you write, you have the body which is originally moving in a straight line with the constant velocity get changing in its velocity. So the body is said to be under acceleration. And such condition, body is under motion called the dynamic state of the body. So that is what you have understood. You need to understand further. At the same time, you can have a question in mind that a body can have acceleration, still it can have a zero velocity. Our body can have velocity, but still it can have zero acceleration. So what do you mean by that is what maybe you'll have that in mind and we will discuss on it, right? So now I'm going to give you an overview, broad aspects of what are that you're going to study in this coming module in my lecture today. So let me share for that board. So all of you are able to see this screen. And I know this is lecture number 33. And today it is 12th October 2020. And we're going to start with the module called dynamics. So when I say dynamics, it is the bodies which are the motion of the bodies which are under acceleration. Dynamics is concerned with bodies that have accelerated motion. That have accelerated motion. Why do I have to write that is because if the motion is exists but it doesn't accelerate, you can't bring that into case of dynamics. Example is straight line motion with the constant velocity is as good as non-accelerated motion of a body. So when the body will get accelerated, when the body is not constrained at all or constrained partially, then there are chances that the body can get an accelerated motion. What I mean by completely free body, non-constrained at all, what do you mean by partially constrained body? So for example, you look at an airplane. So this is in a free body in air. So it is not constrained at all. If it is in the sky, there is no support for it. It's fully free body in space, but it is constrained to have its desired motion. So when this body, which is of weight, flying in air is non-constrained at all, completely free body, but it is under motion, so accelerated motion in air under accelerated motion. So the dynamics of this body is very important in order to go for design aspects of this aircraft. For example, partially constrained body means what? Look at this. So this is the passenger car, which is partially constrained. Weight of this is acting here, where this is like this has got its motion in this direction. This is going to have in this direction motion, and it is now partially constrained. So what I mean by partially constrained, it has got not all degrees of freedom. It can only go in this plane, where this plane is say X and Y plane. Maybe this is the road surface on which it is going. So this is partially constrained, whereas here it is in air is not constrained at all. So it has got total of 6 degrees of freedom. That means it can translate in X direction, it can translate in vertical direction, it can also translate in lateral direction. So 3 translation X, Y, Z, and it can also have rotation about these axes. So that is what the 6 degrees of freedom that this rigid body can possess. And in such a condition, when it is under accelerated motion, you can have the most complex dynamics that is there here. Why? Because to completely describe this, you require Newton-Euler equation. When I do not consider the local deformation of this and I consider this to be a rigid body with the dimensions accounted, then I will use the equations called the Newton-Euler equation. So I will have 3 equations which were required for force balance and 3 equations which are required for moment balance. So we will not go into equation details at the moment, just to understand physically what do you mean by dynamics of a rigid body. So a rigid body which is not constrained at all has got this many number of degrees of freedom. This is called an accelerated body. Even a body which is constrained partially, now it can have only in this direction, or it can go in this lateral direction motion, or it can spin about its axis. Yaw motion it is called. So it can have 3 degrees of freedom on the ground plane. So the 6 degrees of freedom reduced to 3 degrees of freedom because of partial constraint. So vehicle cannot go inside the ground or it cannot fly above. And it can only spin about vertical axis or it can translate in X or in Y direction. So the translation XR in Y direction can be considered to be a component of this motion of the vehicle when it is going in a circular path. So that is how we can understand. So that is again called an accelerated motion of the body. So, so what does that follow? Dynamics means that motion of the bodies which are accelerated, right? So here again you have Newton-Euler equations. So the number of equations here are 6 and here are 3, and you have different coordinate system called body center coordinate system, inertial, non-inertial frame of reference system, and so on. That all we will see that later. I'm not going to bring in more generic at the beginning of the lecture, but we will see in the later part of our study how can we generalize our dynamics. So this is an example of the state of bodies which are not at rest or accelerated, and the dynamics of them is very much important when you have to design such bodies. When you have to design an automobile, the dynamics of that is very important. When you have to design an aircraft, the dynamics of that is very important. So this two particle dynamics can be looked at in a two important categories. One is kinematics, another one is called kinetics. So what do you mean by kinematics and kinetics? So kinematics refers to the study of geometry of the motion alone. Study of geometry of the motion alone without considering the cause of the motion. Whereas what is mean by kinetics is the study of rigid body motion considering the cause of the motion. Correct? So study of system of forces considering cause of the motion. The cause of the motion along with the geometry. With the motion geometry. So this kind of study is important when I look at what is the control strategy of my aircraft or what is the control strategy of my automobile, looking at its motion on the path alone. I'm not worried about what is the cause of the motion. For example, if I see an aircraft navigating in space can have a motion in a trajectory which can be a complex curved path. And a vehicle which is going in a highway, a passenger car, can have to negotiate or adopt itself along with the traffic flow of other vehicles. So if you see, that is my interest of motion geometry alone, I will not be worried about looking at the cause of the motion. I know unbalanced force are necessary, tractive force are necessary, lift and drag forces of our aircraft, all are there, and that is essentially making ensuring the force, the motion. But for the design aspect, if I am not considering the cause, it's only sufficient, the geometry is enough, then I have an advantage of simplifying my dynamics problem. What is that advantage of simplifying my dynamics problem? If I am concerned only with the path of the motion, then not an individual part of the motion. If I say that here, an aircraft, if I look at in air, what is the complex trajectory to fly is my interest. I'm not worried about what is the motion of this wing. So you know that under turbulent state, while aircraft flying, the wings are fluttering. Wings will be oscillating. And the oscillation amplitude, if you look at, it can go beyond 2 meters as well at the ends of the free ends of the wing. I'm not worried about local motion of that. That can, because of that vibration, what it can happen, the aircraft can roll about this longitudinal axis. Sometimes it can pitch. Sometimes it can take a navigation complex contour path. It can have a yaw motion. So such kind of motions which involves locally, if I neglect, I just want to see its path in the sky, being a person observing from the earth, then this entire geometry details won't be appearing for me. It will be appearing to be a small tiny point in the sky, but you know that is very huge structure, aircraft which is flying. In such cases, you look at your dynamics from the ideology that we have looked at, called particle ideology. So I call that kind of kinematics as particle kinematics. Particle kinematics. What I mean by particle kinematics, the physical geometry of the structure is neglected and the path this aircraft follows in sky is only looked at. The path can be a straight path, can be a curved path, can be a spatial curved path. If that is so, its motion on the path is called only translation. I do not look at locally what is the rotation of this aircraft body, what is the rotational part. I am not looking at it because I neglect the geometry of this aircraft. The same thing applicable for a passenger car as well. Like I have the motion of this so that it should not be stopped anywhere. It has to adapt itself and to go with the traffic flow to negotiate its path and go ahead its motion. In such cases, I am interested to look at this passenger car neglecting its physical geometry. So it will be appearing to be a particle. Like you have been observing Formula One race. So you see that there are n number of racers, their vehicles are on the track. So we are so much concerned with what is coming first. So you consider all of them as a particle and that is going in a track. Which particle go ahead than the other if you are looking at. I do not really require to look at the rotational aspects of this and it will go only in the complex contoured path. And that time I can again make my motion study without considering the cause as translation alone. So that will fall in the category of particle kinematics. So for example, I am going to do a design aspects of my automobile. So I have to look at what is that force that is pulling this vehicle on the road. In such cases, it is required that I have to look at geometry of my tire wheel assembly. And then I have to look at what is the driving torque that comes there. So the motion of that automobile, which is described in particle kinematics by translation of the CG, now no more sufficient to design a tire wheel assembly for its motion. So what is that I have to do? I have to draw this tire wheel assembly separately and its free body diagram. So if it is on this floor and it's CG, it goes and then there is a rotation of this and you see here there is a tractive force and there is something resistance force called rolling resistance force and you'll see load reaction here again and the weight that comes on this. So like this, you draw the free body diagram and then you look at its motion. It is not only translation of CG, also rotation is there. So I'll have to look at rolling wheel. So when I look at rolling wheel, which is smaller element in this bigger object, I cannot have my ideology of particle helps me to design. I'll have to get into rigid body kinematics, wherein in addition to translation of this CG of the wheel, I'll have to look at what is the rotation part that comes on this wheel. So if I see that, then I'll call that part of my kinematics as real rigid body kinematics. You can also have an example in the same vehicle, passenger car. Look at the transmission system. It is composed of number of gears. So the gears is smaller dimension compared to that of the total vehicle. But when I have to design my gears and decide number of teeth and what is the fashion of arrangement of my gears in the gearbox, I really require to look at the dimension of them and then go ahead with looking at the other component effect called the rotation. So in such cases, I will look at my motion I'm not worried about cause of the motion at the moment. Motion, and that motion cannot be called as particle kinematics. It has to come under the category of rigid body kinematics. So when I say this rigid body kinematics, I can have this translation, of course, in rigid bodies as well. Why? Because I can say what is the tire wheel translated distance. For one revolution, when it is freely rolling without any driving torque is there, it will be say 2 pi r, you would say. If it is not freely rolling, it is accelerated, then you say it is there is some slip phenomena. So the distance translation, equivalent translation is lesser than that of 2 pi r, you are able to say. That means what? Here I could have translation as well as I will have rotation. So this tire wheel assembly, when it is motion looked at in a passenger car, has got two effects because of its acceleration. One is translation, another one is rotation. You can also have combination of them. Combination of them. That's what is called a general plane motion, GPM. We will see that in detail later. So you can look at suppose a gear. Gear is only rotating. Shaft of the engine, crankshaft, is only rotating. Whereas piston in the engine cylinder, which is reciprocating. You see connecting rod which connects piston and the crankshaft, which is undergoing translation as well as rotation. So like that, you see these all elements I say are the smallest elements in a vehicle. But when I have to consider design of those elements, the dynamics is very important. And the dynamics are to be studied in two categories. One is kinematics, another one is kinetics. So in kinematics, I can have a categories called particle kinematics, wherein a huge physical geometry can be neglected. I am interested only for its translation. But in rigid body kinematics, it essentially imposes as the geometry can be as small as of some few diameter, but you can't neglect it. You should look at that dimension. Then the system of force would cause also rotation, and you need to account is what is imposing on you is what is actual kinematics, rigid body kinematics. But what is essentially important in both the cases, you see that we study them without considering the cause of the motion. I look at only the motion parameters. So how do you define motion parameters and what are the relationship between motion parameters? And based on that, how do we classify the motions further? All is what is now study of kinematics. That is in first hand and one module we will study. Then we'll go into kinetics, wherein we will be considering it is a real dynamics, because addition to this relationship between the motion parameters, we will consider cause of the motion also. So when I say that, I have essentially two equations. One is sigma f is equal to ma, another one is sigma m is equal to I alpha. Right? So these are the dynamic equations. The first equation is called the Newton equation, and the second equation is called Euler equation. So we will see that unbalanced force, and then A or alpha comes from a motion parameter for translation A and motion parameter for rotation alpha. And then we will see problem group here, and we can also write these equation in another convenient forms called work and energy principle or linear impulse and momentum principle for the first equation. Similarly, for the second equation, you have a work and energy principle or angular impulse and momentum principle. All will be looked at in kinetics. And then bodies which are under collision. So you see what do you mean by principle of conservation of energy. What is conservative system of forces, non-conservative system of forces, how their effect on bodies which are accelerated, all we are going to see. Like in the last class, the virtual principle, when you studied, we looked at the connected body system which are under rest condition. There is no motion. So, so you are able to determine the potential energy of the system, and that helps you to apply virtual principle to talk on the static equilibrium position of the connected body system. Same way you can apply them into accelerated motion of the body, wherein you have other forms of these Newton or Euler equations. in our study. So this is what is in brief that you are going to look at in your coming classes, and we will have maybe first 4-5 lectures for kinematics, and then remaining lectures for kinetics to conclude our learning of this course. So now kinematics. So when I say kinematics, you have particle kinematics, and rigid body kinematics. So particle kinematics is actually referring to rigid body kinematics when the rigid body physical geometry is neglected. Physical dimensions are neglected. So because of that, it only deals with the translation. Whereas here it deals with the translation, rotation, or combination of translation and rotation. Okay. So now what are motion parameters? What are motion parameters? Right? So when I say here, this translation can be in 1 dimension, or it can be in 2 dimension, or it can be in 3 dimension. So we call that as 1D motion, 2D motion, or 3D motion, like that. So the 1D motion is what is called a rectilinear translation. Right? Let me have that classification as well here. Rectilinear translation. And if that is in a curved path, it is called curvilinear translation, right? So we are going to study in particle kinematics at the beginning, rectilinear translation and curvilinear translation. So when I say rectilinear translation and curvilinear translation, you can say them as the classification of translation looking at the physical motion of the body which is unbalanced. Unbalance is what is responsible for its acceleration. We don't look at now in kinematics the cause. So motion in straight line is what is rectilinear translation. Motion in a curved path is what is curvilinear translation. So I consider X, Y. This is maybe a ground plane. You can consider vehicle goes over this, you can say. And this is again a straight highway, you can consider in one direction. So this is the physical path. In physical path, you say rectilinear translation and curvilinear translation. So I have here representation of a point which represent a car. I have here representation of a point which represent a car, or if this is space, vertical plane, then it can be an space vehicle, right? If xy is a ground, then it is on a ground. If xy is a vertical plane, I consider that is in the space. But it is constrained to move only in this plane, then it is simplified. If it is constrained to go in the third direction also, then it is 3D motion. But the approach is essentially going to be the same, and we will restrict our study to 1D and 2D motion alone in our course. We are not going to account the 3D motion, right, for the sake of time limitation. But one can easily do it if we are looking at the motion parameters vectorially. I would explain that later on, maybe with some problems. You don't really require to worry about the complex 3D motion. If you are representing vectorially your motion parameters, that would account automatically a complex motion. So now, what is that motion equation? Motion parameters are this. I just want to exactly put those words for you. The motion can be completely described on a straight line by means of its position, this point position. And the point displacement or the velocity or acceleration. So these are the terms called motion parameters. So we are going to look at what are the relationship that is existing with them, as these motion parameters are function of time t. Dynamics, you see that since the state is not stationary, it is changing. We have to look at how the state of a rigid body changes as function of time, is why you get the motion parameters. You can also have a motion parameter which is function of not necessarily explicitly expressed in terms of time, can be also function of space or velocity. That's what we will see, and that's what is called the motion equations. Motion parameters and motion kinematic equations. Motion equations. It's not fundamental governing equation, motion equations of geometry alone, called kinematic equation. So what are those? See, the time is what is important because of this complete dynamics that we say. So if I represent at any point of time, x gives my position of the rigid body. So when I say x gives me the position of the rigid body, what I mean by that? See here, this is the path. The path is straight path, so it is rectilinear motion. And this is now positioned with respect to some origin 0. So I have some reference 0. And from here it is say some distance x, at a distance x. So this x is what is position of this rigid body now from this origin, from the reference point in this straight path, right? So the straight path can be described by means of say this 10 meters, 20 meters and so on. So maybe here it is minus 10 meters, because this is my reference, this is my station point, and from there I look at this forward direction, and this is in the negative direction. I do not consider vertical axis because it is 1D motion, which is straight motion on a highway, right? Okay. So now what is this x? X is what is this position? That is important. If this x changes with respect to time, what would happen? Right? You can say this is the position x at time t, and another time t dash, this has gone to, this is x and this has gone to x dash a. Then the change in position is what is delta x over the time interval delta t. If I consider, then delta x by delta t is what is defining an average velocity. So this delta x is what is in straight line, that is x dash minus x, that is x dash minus x is what is displacement, and the change in position for the given time is what is average velocity, which is given by delta x by delta t. If this average velocity is expressed further as a limiting value, so as this limiting value, then it is called a velocity vector. How do I refer velocity vector? Velocity vector, let me just remove this. Velocity vector, so that's going to be limit that delta t tends to 0. So my observation, instead of appreciable finite time difference, if I look at this t dash is next instant itself, when delta t is tends to 0, then it becomes instantaneous. This becomes simply dx by dt is what is defining velocity vector. And that velocity vector is positive if I consider my moving vehicle particle p, and this is p dash in this direction. So from here in this direction, velocity is positive. If it goes in this direction, it is negative. Velocity is positive to the right and velocity is negative to the right. Position is positive to the right, position is negative to the right. What I mean by position, it's a position vector. If it is in this case, it is described by a position vector. So this is described by a position vector, r vector. So how do I represent r vector now? R vector is xi plus yj. Like that I will represent. So next instant, this is p at time t. Next instant, suppose it is there here, p dash is the next instant at time t dash. This position vector is now r dash. So you will have this delta r vector. So I can have similar way here. The definition of your velocity vector is limit delta t tends to 0, delta r by delta t, which is equal to dr by dt. This is in 2D motion, or it is called curvilinear motion. So that's what one is rectilinear motion, another one is a curvilinear motion. So you define your velocity here like that. So here to define your position, only one coordinate, position x only you are using it. Whereas here to define, you require x as well as y coordinate, and that is what is position vector. So change in position vector over the time difference ratio is what is average velocity when the time difference is limited to approaching 0. That means I look at an instant, and then the derivative of position vector gives you what is velocity vector. So this velocity vector direction, if you look at any point on a curve, in this case it is tangential. So this is my velocity v, and at this point it is velocity v dash, like that. So if I take another point here, the velocity is in this direction. It is always tangential to the path. And here the velocity here is, this is velocity v, and here it's velocity v dash, right? And next instant. So now what is acceleration? Again, like you have defined here an average velocity, you define something called an average acceleration, which is delta v by delta t. What do you mean by delta v? So delta v here is v dash minus v. If v dash minus v is positive when v dash is greater than v. So that means at this instant when I look at my car at position x, the velocity is v. At next instant x dash, t dash instant, the position is x dash and the velocity is v dash. And v dash is more than that of v. That means it is under acceleration. It is under acceleration. And again here I can define this average acceleration as instantaneous acceleration, or simply acceleration vector, as limit delta t tends to 0, delta v by delta t, and that's going to be dv by dt here. And in this case, what would happen? This is v vector and v dash vector, and the average or instantaneous acceleration will be limit delta t tends to 0, here v vector by delta t, that's going to be dv vector by dt. This is the definition of your acceleration. And this v vector has got two components, vx and vy component. Two components like position vector x and y component. You will also have acceleration vax and va component, right? Ay component, like that you will have. So whatever that you have looked at now is a description of your motion parameters, and this motion parameters definition if you have understood, and then you can represent the motion equation, kinematic equation, like that, and it can be always remembered like this. This is its position, one of the motion parameter, and velocity and acceleration. If I look at the radial relationship is what are called the primary motion equation. Primary motion equation. What do you mean by primary motion equation? X is a function of t you are writing, v is function of t you are writing, or acceleration as function of t you are writing. That means it is primary motion equation. You can also express your acceleration as function of this position, velocity as function of this position, or acceleration as function of this velocity. Those are called as secondary equations. So you can express what? You can express your velocity as function of x. You can represent acceleration as function of x, or you can represent acceleration as function of velocity. So these are the three equations which are secondary motion equations. So this is primary motion equation. These are secondary motion equations. So now how do I see this is now how do I express in terms of other motion parameters like acceleration? If I look at it's function of time, but the other parameters will appear in that. That means velocity and this position will appear in the equation. How do we derive that? Is that from this basic definition of your motion parameters, what we have just defined now here, and what we have just defined here for a curvilinear motion. We will see them now in detail further, right? So what is that? After understanding these basic definitions, now we are able to represent what is an accelerated body, what is a decelerated body. Let me just explain you that, and then we will proceed further. So if this is my rectilinear path, straight path, and I have here my reference point O, and my observation of my particle or rigid body is P, where its physical geometry is neglected, P and P dash, and then I say this is accelerated A. When this moves with the velocity v and this moves with the velocity v dash, and v dash is greater than v, then I can say that is acceleration. Right? You can also have the other way. This is my O reference point and P dash. Now you see that V is when can be decelerated? If V dash is smaller than V, then it is deceleration. At that time, you will have deceleration represented in this direction, that's minus A. So that means what? Acceleration is the moving accelerated body in a positive direction, because from here it is positive direction. With increase in speed, magnitude of velocity is what is speed. Increasing speed in a positive direction is referring to acceleration. In the same way, vehicle will be moving in this positive direction only, but it is with the decreasing speed, so that is called a deceleration. So the direction of your acceleration is in this direction, so you have to put minus sign there. So minus A refer here, the particle is moving slower and slower in positive direction. You can also have another way of looking at it. If a particle is moving in a negative direction, and the velocity of the next instant is greater than that of the previous instant, it is accelerating, right? So the acceleration is in the negative direction. You can have positive value of acceleration, where the velocity, where the body is moving in faster and faster, faster and faster, right? If the particle is moving slower and slower, then it is deceleration, whether it is negative direction or not. But what will happen here? You represent that with a minus A. So minus A is not referring to deceleration. Here you represent by plus A in this direction. That doesn't refer to an acceleration. It's a deceleration. So that is very, very important point. That's what I wanted to say. So you should not see the plus or minus sign. Like you look at for velocity, simply with the plus V means it is to the right, minus V means to the left, you can say. But you can't say acceleration plus means to the right, minus means to the left, right? So minus A can refer to acceleration in the negative direction. Plus A will refer to deceleration in the negative direction. Like plus A refers acceleration in positive direction, minus A refers deceleration in the negative direction. So this clarity is very important. So if we have that clarity, now let me go in for deriving some kinematic equation with the motion parameters, with the basic definitions. So what is that? See, when I say here x is function of t, so what is this first equation? We will see one by one in this equation. S is function of t. So how do I represent that equation? Is by uniform motion. So uniform motion, where you have acceleration is 0. acceleration is 0. So it is motion with the constant velocity in one direction. So you may ask, that is a statics problem. Why do we have to say? Because it's important when you go into curvilinear motion, you can have velocity 0, but still acceleration exists. You can say. So this is a case where acceleration is 0, but you have velocity exists. So just to have for that understanding, we call this motion as uniform motion, where acceleration is 0. You can have your x is represented as function of t, and you say that as from this v equals dx by dt. V equals dx by dt. This is how you define a motion parameter, velocity. So if I take dx on one side, it's v dt, and when acceleration is 0, when velocity is constant. You have understood that, because a is what is dv by dt. In the previous slide you have seen, v is what is dx by dt. So when I take the first equation, so this is say 1 and this is 2. From this Roman letter first equation, I could write here x is function of t, and I make v as constant, and that is referring to my first primary kinematic equation, and that results into this. So when I write this, what is this? This is going to be between t is equal to 0 to t equal to some other time, t naught to t. Then I can write this x minus x naught, that's equal to v into t minus t naught. So this is my equation 1 of primary motion equation, 1a of primary motion equation. So 1a, 1b, 1c I have here, right? So now the next equation is what? V is function of t. V is function of t. So what is velocity? Dx by dt. And what is acceleration? Dv by dt. We have just defined. So here v is function of t means I will consider this equation, and let me write that equation as this way. How? Dv equals a into dt. So here I cannot make a 0 because that exists, and if I integrate this between t naught to t and v naught to v, this subscript naught refer to the time. So t naught means initial time, and t is any instant time. So I will have now this a is constant for convenience. This a is not necessary to be constant, because that is what is the third equation says. This is 1b equation. 1b equation. 1c equation is what? A is function of t. This is 1c equation, which is your third primary motion equation. So when a is function of t, when I say this is third equation, the second equation, a can be considered to be constant. So if I consider this a is constant, I can take that out, and this is going to be t minus t naught, and here I will have v minus v naught. So now what is v? V equals v naught plus a into t minus t naught. So initial time is considered 0, then I can rewrite this as v naught plus at, right? T naught equals 0. And then that means what? At t naught, v naught is 0 if I consider. Sorry, v naught is exist velocity, but t naught is referring to time 0 and time t. So I will have this v is equal to v naught plus at, you can write. In your school days, this v naught you write it as u plus at, you are writing it. So this is first equation of a special case. What is it? Constant acceleration motion. That's called uniformly accelerated motion. So this is coming under uniformly accelerated motion. Best example,
Excuse me, sir.
motion under gravity. Yeah.
Sir, actually, sir, I have a quiz in 4 minutes, sir.
Yeah,
So, sir,
you
can
can
you please?
proceed. I have downloaded the attendance. You can proceed. I will finish it in another few minutes and then
Okay, sir.
continue.
Sir, actually, sir, the quiz is starting in 3 minutes, sir.
Yeah, I can proceed. I
Okay, sir.
downloaded that.
Thank you, sir. Thank you, sir. Thank you so much.
Yeah. So this is the equation 1. Let us consider for a special case uniformly accelerated motion. I can also represent now x as function of t. This equation we have this equation I can use. further to get another thing. So how do I do that? We have this and v equals dx by dt together. So I can rewrite that as this dx is equal to v dt, where v is not is going to be function of t if I consider. So I can't make that as 0. So that's again function of t, v of t dt. So this is going to be from t naught to t, and this is x naught to x. So if I integrate this x minus x naught, that's going to be v is now a function of time. So v is function of time is what we have it here. So if I substitute that 0 to t, v naught plus at dt, then I will have here v naught t plus half a t square as x minus x naught. So x will be x naught plus v naught t plus half a t square. So this is my second equation. Again, second primary motion equation. So where x is appearing as function of time explicitly, where here a is constant. That's all for this special case we are deriving. And these two are the two primary equation. When I say in this, a is constant, what will happen if a is constant? I will have this radial line goes out. It's not no more function of time, and I will have now only two time equation. X is function of time or v is function of time. So a is constant. So two primary motion equation and then one secondary motion equation. What is that one secondary motion equation? Because a is constant. When a is constant, it is independent of x, independent of t, and independent of v. So this side, all this disappears. I will left with only x function of t, v function of t, or v function of x that I can write. Those are the three primary motion equation for the second category called uniformly accelerated motion. So how do I get that? Is from this. So I have now my basic definition of velocity as dx by dt, and I have x as velocity as dx by dt and acceleration as dv by dt. From these two, if I eliminate the dt, I can express my acceleration as v dv by dx. That's important. That's important. So what is dt? Dx by dt. What is v from this? Dx by v. Dt I take it on this side, dx by v. And if I put that here for dt, I will have v dv by dx. So this is the third important definition of relation between this motion parameter. So if I have this, and then if I plug in a, this is value is constant. If I plug into my equation, right, I can have through integration the third governing equation. What is it going to be? So I have now a is represented now v dv by dx. So let me take dx on the other side and v dv and integrate this from v naught to v. So here the time is not explicitly appearing. That's why it is called the secondary motion equation. But what is v naught at t is equal to 0? What is v? Is what is v naught? And t is equal to t, what is v is this? So at that time, position is x naught and x, and you consider, and a happens to be constant here because uniformly accelerated motion. And then I can write this as a into x minus x naught. On this side, it is going to be v squared by 2. So v squared by 2 minus v naught squared by 2. So I will have v squared is equal to v naught squared plus 2a into x minus x naught. So this is your third equation for uniformly accelerated motion, which we have already studied in your school days. And these are the three equations for motion under gravity. So we have so far seen four equations. For uniform motion, we have seen only x is function of time. So where you define the x minus x naught is equal to v into t minus t naught. T naught is 0, it is simply vt. So x minus x naught is Vt. So x is equal to x naught plus Vt is what is the equation for uniform motion. And for uniformly accelerated motion, this third equation, which is implicit equation. So what is that? V is represented as function of x, right? Third equation. And the two other primary motion equations are V equals V naught plus At. And other equation x is equal to x naught plus V naught t plus of At square. So this is equation 1, 2, 3 for uniformly accelerated motion, which is in translation category, and uniform motion here, this one equation. Right? So you can have a condition if A is not constant, then what would happen? Then you'll have 6 equations. Right? So you will also have A is function of time. So you do not be explicitly able to derive an equation because A is varying there. Then you will have to seek the motion curves. Of course, you can also draw motion curves here, and you require to draw motion curves in order to have the relationships. So A is function of t, and A can be function of v, and A can be function of x. So these three equations are generic form for when acceleration is varying. Because further also you have it. When you have these three, you have all the 6 equations. So that's the conclusion. So all the 6 equations. For all the 6 equation for acceleration is not constant motion. If acceleration is constant, the 6 equations become only 4 equations. Which are those? You have only till 4 equations, 1, 2, this is not there, this is there, 3. So these are the 3 equations, right? When acceleration is constant. When acceleration is 0, you have only one equation, that's this first equation. So that's what you should understand. And I will stop at this point of time now, and then we will continue with the looking at this motion parameters for curvilinear motion, and then take up some problems to solve to confirm our understanding. So in the next class, I'm going to teach you something called what is this motion curves that I'm ending here. So motion curves are the variation of A as function of time, variation of V as function of time, and variation of position as function of time. If I draw the plot of them, that's a primary motion curves. I can also plot a variation of A as function of V, or variation of A as function of X, or variation of V as function of X. These are secondary motion plots. So you have now the variation graphically looking at them is what we will see in the next lecture, right? If there are no doubts, I'll stop at this point of time to go ahead.
Okay, sir.
Yeah.
Can we do a short question?
Yeah,
Sir,
Shaktiman.
so we can.
Yeah, tell me what is the doubt, Shaktiman?
Sir, DA question, sir. DA2 question.
Yeah, DA2 question I will post it because that's see I have to organize what is that I'm going to deliver accordingly. I'll have to post it. That's why I'm taking some time. I needed some time, but I will post it and accordingly give you the time. See, your DA2 submission is that last day of instruction, right? So we will change that to the last day of instruction. 6th November is the last day of instruction. So I will post it and then you have a time, sufficient time. Maybe in another 1 or 2 days, I will group some 20 problems to 25 problems and that will be your DA2. Okay. But parallelly, you have to come along with me so that I will conduct any time a quiz. At that time, you should be able to answer what is currently you are learning in the class. Yeah.
It means, sir, that can be extended, no, sir? Last date. That DA submission.
No, that's normally last instructional day. That cannot be extended. Now, whatever the time given, 23rd October will be extended.
Oh, that time actually. Okay.
Yeah. So we have our semester in between a break for a week, and our last instruction day is 6th November as of now. So I will extend it in case it is not possible extending in VTab. I will give you sufficient time to post it in Microsoft Team itself. So you may submit
Okay,
your
sir.
files. I will do that.
Okay,
In
sir.
arrangement. Yeah.
Sir, which will be in MCQ form or what, sir?
Yeah, it can be MCQ or descriptive, small questions. That depends on the time of announcement. You have to be ready for both, right?
Okay.
Yeah.
Yes.
Yeah. So if there are no doubts, I'll stop at this point of time. I'll stop recording.